All right, y'all, this is note card number 3. It says analytical strategies for finding limits. So what Stacy McMullen tells us, some steps, when you're trying to evaluate a limit without a graph, we're going to try direct substitution, and then we're going to try factoring and canceling. And then if neither of those work, we can try some special trig limits, which we'll look at if we come to it. So let's try the first one here. Now, on these note cards, if you see some asterisks, these were actually former questions on former AP tests, the real tests. So, all right, so the first one, I'm going to try step 1, try direct substitution. So if I plug in pi, everywhere I see it says the limit of this function as theta approaches pi. Everywhere I see a theta, I'm going to plug in pi and see if that does the trick for me. So if I do that, I get pi times the secant of pi. Now this would not be an answer choice if this was the actual calculus test. Let's rewrite that. Okay, I should know that secant is the reciprocal to cosine. So it means this. And from the unit circle, you should know that the cosine of pi radians, if you think about the unit circle, pi radians is the same thing as 180 degrees, so you're over there. Okay, and the cosine of that's like the x value. The x value of this point is -1. Okay, well, 1 divided by -1 would be -1, so you have pi times -1, which equals pi. So the answer there for number 1 is pi. All right, number 2. If I try to plug in 1 real quick, well, 1 squared is 1. 5 times 1 is 5. So you would get 1 plus 5 is 6, minus 6 is 0. 1 minus 1 is 0. And you know you're not allowed to divide by 0. So if I try direct substitution, that's not going to work. So what I should do next is I should try to factor and cancel. Okay, so if I factor the numerator, well, when I do this, I need to rewrite the limit statement. The top's going to factor into x plus 6 times x minus 1. The denominator is simply an x minus 1. Now here you have an x minus 1 in the top and the bottom, so we can cancel those. Now, since I've simplified that, this just becomes a limit as x approaches 1 of x plus 6. If I plug in 1 here now, 1 plus 6 is 7. So that's the answer. And the reason this works, remember, a limit is as you approach 1. If you actually go to 1, there would be a hole there. There would be a removable discontinuity. But as you approach 1, we're going to be approaching a y value of 7. Okay. Number 3, first thing we try to do is we try direct substitution. So if I plug that in, everywhere I see an x, I'm going to plug in pi 6 radians. Okay, now what is pi 6 radians? Pi 6 radians is like 30 degrees. Okay. If you use your fingers, you pull back your 30 degree, and here's my cosine. It's over here. I got 3 fingers. So that's going to equal square root of 3 over 2. That's the answer there. All right. Number 4 says, as long as a doesn't equal 0, what is the simplification of this? So if I tried to plug in a right now in the numerator I would have a minus a, which is 0. If I plug in a to the denominator everywhere I see an x, a to the 4th minus a to the 4th would be 0. So that doesn't work. When I try to plug in this value, I get 0 over 0. And you can't divide by 0. So we have to try number 2. We have to try factoring and canceling. Okay. So if I do that, let's just go through the steps here. I'm going to leave the numerator as x minus a. Okay. But this right here is the difference of 2 squares. Okay, how do I get that? Well, I have x squared minus a squared and x squared plus a squared. If you FOIL that out, you would get back to this whole thing. Now that can be simplified some more. This part cannot be simplified anymore. So that part's done. I can't do anything else with that. But this part will actually break down into two other things. That'll break down into simply x minus a times an x plus a. Okay. So I'm just going to scratch that out because that's another difference of squares. Now it's x minus a times x plus a times x squared plus a squared. At this stage, now I can cancel out these x minus a's. Now what happens when I plug the a in? Okay. Well, everywhere I see an x, I'm going to plug in an a. So I get 1 over a plus a. And I plug in a here, and I would get a squared plus another a squared. All right, and that can be simplified. A plus a is 2a, and a squared plus a squared is 2a squared. Now if I do that multiplication, 2 times 2 is 4, and a times a squared is a cubed. So that becomes 1 over 4a cubed. And that's as far as we can take it, because we don't actually know what a is. A is some number. They're not telling us what it is. Okay, let's look at number 5. Now, this is a piecewise function. Okay, that's a piecewise function. Now, the first part is a parabola, 2x squared minus 3. And that is the function that we use as long as x does not equal negative 4. But when x equals negative 4, we get 1.7. Okay. So here's what it would look like if we were to plot this out. Okay, if you actually plug in negative 4 here, negative 4 squared is positive 16. 2 times 16 is 32, and 32 minus 3 is 29. So when x is negative 4, okay, the parabola would be getting close to here. So if you were to graph this parabola, it might look something like that. Okay, now why did I put the open circle here? Because this function is good for everywhere except negative 4. When x actually equals negative 4, the y value is 1.7. Okay, so that's like 1.7. Now the question is about a limit. The limit is as we approach. So as I get closer and closer to negative 4 from the right, the function's approaching this y value. As I come in from the left, it's approaching that same y value. It doesn't matter that that's the filled-in circle. Okay, it's what value is getting approached, what y value is getting approached, and that happens to be 29. So here, the right answer would be 29. So if you see a piecewise function like this, this part does not matter. It doesn't matter what x equals, or it doesn't matter that the actual function value at negative 4 is 1.7. It matters what it's approaching here, and it's approaching 29. So that is the correct answer. Okay. Now, let's look at number 6. Number 6, if I try direct substitution, if I try to plug in 0 here, 5 times 0 is 0, sine of 0 is 0, 2 times 0 is 0. So if I try direct substitution, I get 0 over 0. So method 1 won't work. Now there's really no way to cancel anything. Okay, these x's cannot be canceled because the 5x is an argument of a trig function, and this is just a polynomial on the bottom. So options 1 and 2 will not work. Okay, but at the top of the paper, this right here, the limit as x approaches 0 of sine of kx over mx is simply going to be k over m. So whatever that coefficient is inside and whatever the coefficient is here, that's going to be the solution. That's going to be the fractional answer. So this one is simply going to be 5 halves. Okay, and eventually you're going to learn a way to do that that's really easy. And we're going to learn something called L'Hopital's rule. And that's going to help us do this a lot quicker. So you don't really have to remember this rule up here. We're going to learn a simpler rule, and it'll be real easy. All right, now let's do number 7. Number 7, it says if g of x equals 3x cubed minus 5, then what does this equal? Well, let's try some substitution. So if I just try to plug in 0 everywhere I see an x, let's see what we would get. Well, here g of 0 minus the same thing is going to be 0, and 0 cubed is 0. So method 1 will not work. So now we're going to try to do some substitutions. Okay. So up here in the numerator, I see a g of 0. So let's figure out what g of 0 is. That means everywhere I see an x, plug in a 0 to this function. So this would be 3 times 0 cubed minus 5. And if we keep simplifying, 0 cubed is 0, 3 times 0 is 0, and 0 minus 5 is negative 5. So we could plug that in for g of 0. So let's rewrite this limit. We can do one more thing, actually. This is simply a g of x. So we know what that equals as well. That equals that. So I could write 3x cubed minus 5, that's what g of x is, minus, well, I know what g of 0 is. That's the same thing as negative 5, all over x cubed. And we can do some simplifying here. 3x cubed minus 5, and then you got two negatives next to each other, which turns into a positive. Okay. We got a negative 5 and a positive 5. Those cancel each other. They sum to 0. So now I have a limit as x approaches 0 of 3x cubed over x cubed. And you should realize, well, x cubed over x cubed cancel each other. And now, when you're down to this, the limit as x approaches 0 of just 3, when the limit as x approaches anything, if this is a simple constant, then that's what the answer is. And that's what the answer is. So the answer here is simply 3. Let's try some more. All right. So in number 1, if you try the first option, actually you can try these on your own, stop the video and see if you get the same things that I get. Okay. If I plug in negative 2 to start with, I would get a 0 in the denominator. You're not allowed to divide by 0. So we would have to try some factoring. So I can rewrite this as, if I do some factoring, I get x minus 6 times x plus 2 all over x plus 2. The x plus 2's cancel each other. And now you can try to plug into the simple x minus 6. Negative 2 minus 6 is negative 8. That's the answer. Okay, number 2 was just like the problem we just did. Okay, if I figure out what r of 0 is, negative 5 times 0 squared plus 4. 0 squared is 0. Negative 5 times 0 is 0. So this is simply going to be a 4. I can rewrite this. I can make a substitution for r of x. That's the same thing as negative 5x squared plus 4 minus r of 0 is simply 4 all over x squared. Positive 4 and negative 4 sum to 0. And negative 5x squared over x squared, these x squareds would cancel now. And I'd be left with a simple constant. So my answer here is negative 5. All right, number 3, first thing we try to do is direct substitute. So when we do that, secant of negative 4 pi over 3 And we don't really like that so much. We're going to rewrite it as a cosine. Now we have to think about where that is on the unit circle. Negative 4 pi over 3. Well, if you want to think about degrees, pi radians is like 180 degrees. If you want to think about that, this is just some side work. And 180 over 3 just becomes 60, so that's negative 240 degrees. So if you're going negative degrees, instead of going counterclockwise like we're used to, we have to go clockwise. All right, so if you're going negative amount of degrees, this would be negative 90, negative 180, and I have to go 60 more. So on the unit circle, my reference angle becomes a 60. Okay, so think about your reference angle being 60. Pull back your 60 degree. Okay, well, what's the cosine there? I only have one finger. I only have one finger here. But you are in the second quadrant. So this point on the unit circle, it would be negative 1/2 because you're to the left of the origin, and you would go up square root of 3 over 2. That's what the point is on the unit circle. Now, which one of these is the cosine value? It's this one. It's the first one. It's the x value. So this becomes simply 1 over, what is this quantity? It's this, negative 1/2. How do you take care of that? Keep the top the same, change division to multiplication, and flip the next fraction. All right, which becomes 1 times negative 2. Therefore, the answer is negative 2. Now the next two problems are a little bit harder. There's different ways to do it. So we have 3 pieces here. Let's actually start with part B. The limit as x approaches 0 of g of x. So look at your domains here. Where would 0 fall? Obviously 0 would fall in this piece because 0 is between negative 2 and 3. So we can just try direct substitution there. We can plug in 0 here. 0 squared minus 5. So that's what that's going to be. It's going to be 0 squared minus 5. 0 squared, 0. So that part's relatively straightforward. That's negative 5. Now, what about this first one? What about part A? The limit as x approaches negative 2. Well, that happens to be a cut point. This function applies to everything to the left of negative 2. This function applies to everything to the right of negative 2. Okay. So pick a number to the left of negative 2. Well, let me say it a different way. Let's figure out what the limit as x approaches negative 2 from the left is. So when it approaches from the left, we're going to be using this function. Okay. So if you try to plug in negative 2 here, negative 2 plus 2 is 0. So that doesn't work. You're not allowed to divide by 0. Pick a number that's really, really close to negative 2. A little bit less though. So maybe like negative 2.01. Okay, so let's just kind of write an approximately equal 1 over, plug in a number really close to negative 2, but a little bit to the left of it. Okay, so if you do that, you get 1 over negative 2.01 plus 2 would be negative 0.01. Okay. which would be, if I divide this by this, I would get negative 100. What about if I picked a different value? What about if I picked 2.001? Then that would become negative 1,000. What about if I picked negative 2.0001? And that would be 10,000. So what this is actually going to be, it's actually going to approach negative infinity, which is not a number. So we would say does not exist coming in from the left side. Okay. Now what about as I approach from the right side? Well, if I approach from the right side, I can try to plug in negative 2 to this function. Negative 2 squared is positive 4, minus 5 is negative 1. Okay. Obviously, these two things do not equal each other, so it does not exist. Now that's kind of hard to see. It's kind of hard to understand. So let's look at a graph of this piecewise function. Let's kind of think about this real quick. Let's look at this one. X squared minus 5, but that's only good between negative 2 and positive 3. So if I plug in these values, when we plug in negative 2 here, negative 2 squared minus 5 is negative 1. Okay. When I plug in 0 here, 0 squared minus 5, that would be negative 5. Okay. What would happen if I plug in 3? 3 squared is 9, minus 5 would be 4. Okay, and there's a bar underneath there, so 3 is included. That's why I put a dot. Okay. So there's the parabola piece. What about this first piece? This first piece is only good for x values that are less than negative 2. This is actually a rational function. So if you remember about that, that actually is going to create an asymptote. There's a vertical asymptote at negative 2. There's actually a horizontal asymptote at 0. So if you were to graph this function to the left of negative 2, it kind of looks like this. Okay. And then you would have a part right here if you didn't have the domain restriction, but we do have the domain restriction. All right. So if you want to think about this graphically, hopefully you see as you approach an x value of negative 2 coming in from the left, you're going down towards negative infinity. As you approach negative 2 from the right, you're getting close to a value of negative 1. Okay? So negative infinity does not equal negative 1. So since the left limit does not equal the right limit, we can simply say here that the limit does not exist. That's what we would say there. Now what about the last piece here? All right, what about, going back to part B, as I get close to 0, what am I doing? As I get close to 0, coming in from the left and coming in from the right, I'm approaching a value of negative 5. That's why part B is negative 5. And lastly, okay, now the whole purpose is analytical. What about as we approach 3? What about as we approach 3? And actually, this is just, I think it says 3 coming in from the left. Well, as I approach 3 coming in from the left, I would be using this function. I'd be using the middle function because this is the middle function. That's what it would be coming in from the left. So on the graph, as I get close to 3, they want to know, what am I approaching right there? Well, we've already figured that out. That's just 4. So as I approach 3 from the left, I would be using the middle function here, And I would just be plugging in 3 to the middle function. 3 squared minus 5, 9 minus 5, which is 4. Now, even though it doesn't really ask for it, let's figure out what the limit as x approaches 3 coming in from the right is. As I come in from the right, I'd be using this last function. So first thing we try to do is direct substitute. So 3 plus 13 is 16 underneath the square root, which is also 4. Now here, the left limit and the right limit are the same. The left limit and the right limit are the same. And what would this graph look like? Well, it's just a radical graph. So it would kind of look like that from there on. And if they were just asking for the limit as x approaches 3, both of these are approaching the same y value. They're both approaching 4. So even if we got rid of that minus sign, since these are the same number, the limit as x approaches 3 is simply going to be 4. Now the whole purpose behind this is not really to necessarily have to graph, just to do it analytically. So let's look at problem 5 here. It says another piecewise function, all right, ln of x, and that's only good for x values between 0 and 2, and the 2 is included, okay? So they're asking me for the limit as x approaches 2. So when I come in from the left side, I'd be using this function. Okay. So the limit of f of x as x approaches 2 coming in from the left, I would plug in 2 to there, ln of 2. And that's just going to be some decimal number. Now what about as I approach from the right? When I approach from the right, I'm approaching from bigger values than 2. So I would be using this function. Okay, so all I do there, the first thing I try to do is direct substitute. So everywhere I see an x, I'm going to plug in 2. So 2 squared times ln of 2. 2 squared is 4. So that's 4 times the natural log of 2. Now, do these things equal each other? Does the natural log of 2, which is some decimal, equal the same thing as 4 times the natural log of 2? Well, this is 4 times greater. This is not 0. Okay, it's not ln of 1, which is 0. Okay, these things are different. So therefore, the limit, in order for the limit to exist, both the left limit and the right limit have to be the same. These are not the same number. Okay, and if you're not sure, if you just plug it into a calculator real quick. All right, if I type in ln of 2 into my calculator, it's about 0.69, and 4 times natural log of 2 is 2.77. And that's 4 times greater than that. These do not equal the same thing. Now, just to kind of show you, all right, remember we can graph these. I'm just going to do it in the calculator. I do ln of x. That's only good between 0 and 2, so it's only good when the x values are greater than 0 and the x values are less than or equal to 2. And I can graph the second piece, x squared ln of x. That's only good when the x values are greater than 2 and the x values are less than or equal to 4. All right, on my window, I'm just going to go from 0 to 4 on my x values. And I'm going to let my calculator, then I'm going to go zoom fit. So there's the first piece, and there's the second piece. Okay. So that was the ln of x part, and this was the x squared ln of x part. As you see, as you approach 2 from this side, and as you approach 2 from this side, you're getting close to that y value, which we saw was 0.69, around 0.69. As you come in from this side, you're approaching about 2.8. And you can even hit trace. Okay, that's the 0.69. And sorry, about 2.9. Okay, there's a gap there. They're not approaching the same y value. All right. But we didn't have to graph. We could just try analytical methods plugging in. And that was the whole point. All right. There's another problem here. It says the graph of f of x is shown in the figure below. Which of the following statements about f of x is true? Okay, so let's look at each one and try to eliminate some answers. All right. Here in part A, they're saying the limit as x approaches 1 does not exist. Well, here's my x value of 1 right there. As I get closer and closer and closer to 1 coming in from both sides, it does look like they're approaching the same y value. They're both approaching 1. This is wrong because the limit actually equals 1. So that's not true. Now let's read the next one. The limit as x approaches 2 from the right equals 0.3. So as I'm coming in to this graph, 2 from the right means I need to come from the right side. So I'm approaching here. And what's the y value there? Is it 0.3? No, to me it looks like it's about 2.7. So if that said 2.7, it would be correct. But that's not. It doesn't say 2.7, it says 0.3. Right. So part C, it says the limit as x approaches 2.01 is less than the limit as x approaches 0. Well, as I approach 0, okay, here's an x value of 0. As I approach 0 from both sides, that's the y value that I approach. Maybe it's about 2.3. Okay, so this part of it would be 2.3. But as I approach 2.01 from both sides, we've already figured out what that was. That's about right there. And we said that that was 2.7. Okay, so here, ask yourself, is 2.7 less than 2.3? Hopefully you say, well, no, that's not true. Now, what about this? Let's go to E real quick. The limit as x approaches -3 equals 4. Well, as I approach -3 from the right, it most certainly is 4. But there's nothing over here. I don't know what's happening over here to the left of -3. This is a two-sided limit. It doesn't just have a, if it had a plus sign, then that would be true. But it doesn't have a plus sign. So the only way this is true is if the right limit equals the left limit, but there's nothing going on to the left. So that's what makes this false. So by process of elimination, this has got to be true. Okay. Here it says the limit as we approach -1 from the left is the same as when we approach -1 from the right. So as I approach -1, all right, here's my -1. All right, as I come into that, coming in from the left, it looks like I'm hitting 3.5, about 3.5. So I'm coming in from the right, it also looks like I'm getting closer to 3.5. Okay, so because both of these are the same, since the left limit equals the right limit, the limit exists. Okay, and that makes this absolutely true. That's the one that's true. Okay. So part 7 says using the table below, find the limit as x approaches 1. So let's think about it. As I'm coming in close to 1 from the left, look at these numbers, -2.689, negative 2.6, negative 2.611. So to me, I think the limit as x approaches 1 coming in from the left would equal about negative 2.6. Now what about as I come in from the right? As I come in from the right, I'm looking at these values. 2.61, 2.601, 2.598. So to me that looks like it's about positive 2.6. Now in order for the limit to exist, these numbers have to match each other exactly. Do they? No, they don't. One's negative, one's positive. So therefore the limit simply does not exist because these two do not equal each other. So that's the end of the notes. So your packet, okay, you have a few things here. You want to evaluate limits using those skills. So first thing, try direct substitution. If that doesn't work, try to factor and cancel or to use one of those special trig limits. And then there's some more practice here with using this graph to find some of these stated limits. And you got some more problems here, okay? You got some piecewise, and then you also have to evaluate these two by looking at the graph, or you can look at the functions themselves. It's not too hard of a packet, it's pretty short. It should take you about 15 minutes or so. So just give that a shot tonight.